In this video, we're going to go ahead and cover section 9.3, geometric sequences and series, part of unit 9, sequences, series, and probability. We've already covered the arithmetic one, so it's a lot more formulaic stuff, but now instead of adding or subtracting a common difference, we're going to be doing something that's called a common ratio, where we're actually multiplying by something, or you could think of it as division if you're going the other way, okay? So formally, here is the definition. A geometric sequence is when the ratios of consecutive terms are the same. So if you divide one term by the other in that order, you should get the same thing, basically. Okay, so we have a sequence a sub 1 through a sub n and so forth. It's considered geometric when there's a number r, such that if you divide the second term by the first term, it's the same as if you divided the third term by the second, fourth by the third, and so forth, to give us that common ratio, okay? The number r is the common ratio of the geometric sequence. So we're going to go ahead and go right into an example. I went ahead and kind of did a back and forth thing for this one, so you have some that are done, some that we're going to do together. We have this first one here. It says, write the first four terms of the geometric sequence whose nth term is given by this, 6 times negative 2 to the nth power. Then find the common ratio of the consecutive terms. So what I did here, and you can kind of see the work, is I actually plugged in all of my n's. So for n equal to 1, we have 6 times negative 2 to the first power, which is just 6 times negative 2, which is negative 12. So negative 12 is our first term, a sub 1. You do the same thing for 2, 3, and 4. I'm not going to go through the whole math. It's kind of, you can just follow it along. But we plug everything in into our n term right here. And these are the numbers that you get. So first term is negative 12, second term is 24, third term is negative 48, fourth term is 96. You'll notice that the signs are switching, so it's probably going to be some kind of negative ratio. Okay, and if you look down here, I actually went ahead and set it up for us where r is equal to, and I followed the exact same pattern, second term divided by the first term, third by the second, fourth by the third, plug in those values. So these values are coming from this right here. And you'll notice that all of these are equal to negative 2. 24 divided by negative 12 is negative 2. Negative 48 divided by 24 is negative 2. And 96 divided by negative 48 is also negative 2. So these are all equal to each other, and that is our common ratio. R equals negative 2. The sequence officially, we have our numbers listed here with some dots because it is going to go on forever. And that's it. That is it for the first problem. So pretty simple. Let's look at the next one. We have another kind of, I don't want to say definition, but something else to copy. Okay. The nth term of a geometric sequence. So this is when we are looking for, excuse me, we might be given some term and we need to find some term later on in the sequence, okay? But it's given by the following. A sub n, this would be the nth term, is equal to a sub 1. Let me get this to focus a little bit. So the first term times the ratio to the power of n minus 1, where r is the common ratio of consecutive terms, just like we kind of saw in the one before. So basically, every geometric sequence can be written as the following using this. Our first term, and the first term times r, the first term times r squared, the first term times r cubed, and so forth, all the way till we get to the rn minus 1, which is where this is coming from. Okay, so one little note here, then we'll go into the example. It says, when you know the nth term of a geometric sequence, multiply by r to find the n plus 1th term. That is the following right here. Okay, so here we go. We're going to go ahead and do example number 2 together. It says, write the first 5 terms of the geometric sequence whose first term is a sub 1 equals 2, and whose common ratio is r equals 4, then graph on a coordinate axis. So we're actually going to graph, well, it's more like a scatter plot, but we're going to graph this one afterward just so you can kind of see visually what a geometric sequence might look like. And I'm sorry you can see the notes over here. Don't worry about those for now. So let's see how we're going to do this. We know that r is equal to 4, a sub 1 is equal to 2, and we want the first 5 terms of this. So that means I'm going to go ahead and just kind of use my formula here. Remember, here it is, a sub n equals a sub 1 times r to the power of n minus 1. Looking at it real quick. We're going to use this, and we're going to find the first 5 terms. So a sub 1, well, we already have it, right? It's just a sub 1 times our ratio, which is 4. Oh, I'll plug it in right now. To the power of n minus 1. So 1 minus 1 is just going to be 0. And we know that a sub 1 is actually given. It's just 2. So we have 2 times 4 to the power of 0, which is that's just a 1, okay, which is just 2. So this is just kind of proving that this is indeed equal to 2. Okay, a sub 2, so the second term is going to be a1. So a1 is equal to 2 times our common ratio 4, and then n minus 1, so 2 minus 1, like so. And we're just going to simplify that. So 2 times 4, 2 minus 1 is just 1. So 4 to the first power is just 4, 2 times 4, and that's going to give us 8. Okay. The third term, we have 2 again, because remember, a sub 1 is 2. We have to use a sub 1 always for this one. Times 4 to the power of 3 minus 1. So we're looking at 2 times, let's see, 4. 3 minus 1 is 2, so 2 times 4 square, which would be 4 square is 16. So 2 times 16 is 32. Okay. Fourth term, we're almost done. We have 2 times 4 to the power of 4 minus 1, which would be 2 times 4. 4 minus 1 is 3. Okay, so we have 4 cubed, which I believe is 64. Okay, 2 times 64 is 128. We are on the last term, fifth term. So 2 times 4 to the power of 5 minus 1, which is 2 times 4 to the fourth power, which is 2 times 4 to the fourth power is like saying 4 times 4 times 4 times 4, which I'm going to do in my head as 16 times 16, which is 169, I believe. Okay. And then, oh, actually 16, no, hold on. 1 second. Maybe I misled here. 16 squared, we're doing, that's going to be 6. 216 is 12. 1. Oh, I'm sorry. It's 256. What am I saying? What am I saying, Miss Lorana? 256. Okay, I just did a quick, for those of you who are interested, this is a super quick trick. This is going to be 6 squared is 36, carry the 3. 6 times 1 is 6, double it is 12, plus 3 is 15, carry the 1. 1 squared is 1, plus 1 is 2. Number sense tricks for you all. Anyway, side note. So 256, okay, and then 2 times 256 is going to give us, let's see, 4, 250, 512. Okay, and I believe that that's it for those. So these are the terms. Okay, we have the first 5 terms. So 1, 2, 3, 4, 5, all these, and they want us to graph it. So I'm just going to do a quick little sketch right here, just a quick sketch, which would be, oh, I'm just going to kind of eyeball it too because I don't really want to go too crazy. So 1, 2, 3, 4, 5. And we're just going to go by, let's see, we have 2 all the way to 500. So I'm going to go by hundreds. So 100, 200, 300, 400, and 500, something like that. 1 is very, very close to the axis. It's practically 0. It's at 2, so it's somewhere down here. 2 is still pretty down there also because it's just 8. 3 is 32, so it's about a third up from to 100. 4 is 128, so it's a little bit over 100. And then 5 is 512, so it's like way up here somewhere. So you'll notice, we're not going to connect it, but you can kind of see the pattern is growing almost, it looks like an exponential function almost, right? And that kind of makes sense because we have in our formula here, we have a power, yeah? So it's probably going to rise significantly, okay? But anyway, that is it for that one. Moving on, next one. Hopefully I did all the math right here. Okay, so move on to the next one. We have example number 3. It says find a formula for the nth term of the geometric sequence 4, 20, 100. And then what is the 12th term of the sequence? So for this one, we need to, it's kind of like the one before, but we do not have the common ratio. Oh, excuse me, I'm a little tired today. We don't have the common ratio, so we have to find the common ratio. So we need to find R first. How do we do that? Well, we remember that R is equal to a sub 2 over a sub 1, which is the same as a sub 3 over a sub 2, a sub 4 over a sub 3. Basically, these things divided by each other, but consecutively in order. So you can kind of think of it like we can take our second term, 20 divided by 4. Or we can take the third term, 100 divided by, well, the one before it, 20. And these should be the same. So let's see. 20 divided by 4, I believe that is 5. 100 divided by 20, that is also 5. So it looks like R is just equal to 5. Our common ratio is 5. Okay. So now that we have the common ratio for the formula, remember that it's a sub n equals a sub 1 times R to the n minus 1 power. So we're just going to plug in what we know. We know that we don't know a sub, this will be a sub 12. We know a sub 1 is the first term, so a sub 1 is 4 in this one. So 4 times my common ratio, 5, to the power of n minus 1, so 12 minus 1, which is going to be 4 times 5 to the power of 11. Now, obviously for this, you are going to need a calculator. I'm not sure if you can use Desmos. Let me do that real quickly right now, and we will check. I know I can do it on my calculator, but you guys don't have that calculator. So let's get that up and going very quickly, as quickly as I can get it to work. And here's Desmos. Okay, so let's see. I'm going to go ahead and do 4. Oh, let's not switch it like that. We're going to do 4 and then times 5. And we want this to the power. That's going to be this button right here, A to the B, 11. And oh, it does work. There it is. It's that humongous number, 195312500. It's actually 195 million. So let's do that. A sub 12 equals 195,312,500. That is a pretty big number. But there you go. There is our 12th term of the sequence. Okay, moving on to example number 4, which I believe is solved for us because of the time. So we have example number 4, the second term of a geometric sequence, and here's the answer, but read it first, is 6, and the fifth term is 81 over 4. Find the eighth term. And I ran out of whiteout, so I couldn't fix this, but this is 8, the eighth term. So for something like this, you kind of have to think a little bit because we don't have the actual sequence. But we do know that the second term is 6 and the fifth term is 81 over 4. And these are 3 terms apart from each other because 5 minus 3, I'm sorry, 5 minus 2 is equal to 3. That's where this is coming from. So you'll notice that in my formula, what I did is I went ahead and set this equal, and this kind of goes back to the note we made on the page before, okay, where you're multiplying. Here, let me show you this part right here. A sub n plus 1 equals a sub n times r, that one. Where r, depending what we're looking for, we have to raise it to the power, okay? So here's how it works. We will take that 3, and that's going to be the power that we're going to put for r, and then we're just going to set these equal to each other like this, and you put the bigger one first, obviously, okay? You will notice, actually, let me do like an extra step here. A to the fifth is 81 over 4. I'm sorry, not a to the fifth. The fifth term is 81 over 4. The second term is 6, and then r, we don't know what it is, so we just kind of did that because we're trying to solve for r, okay? And from here, I went to this step. So I was trying to get r by itself to solve for it. So I divided both sides by 6. If I divide both by 6, you put a 6 here, and that goes away. And it's kind of like multiplying this one by 1 over 6. Okay, that's all you're really doing. So if you do this right here, we get 81 over 24 is equal to r cubed, because that went away to 1. And then from there, I simplified it because, well, this is kind of a big number, right? So 81 and 24 can be divided by 3, which gives me 27 over 8. And I know that this one right here is a perfect cube. So what I did here, and I didn't put it here, but I'm going to mark it now, is I cube rooted both of these. Cube root means basically you're trying to find a factor that is the same 3 times being multiplied. So 27, for instance, here kind of a side note, 27 is the same as 3 times 3 times 3. So that's the group that you're looking for. So there's 3 for 27, and for 8 it's going to be 2. So r is equal to 3 over 2, or 3 halves. So now that we have our ratio, we can go ahead and plug everything in. Um, and I don't have the first term, because usually when you have the r and the first term, you can just plug them into the formula, but we don't have that. So we're going to use the same thing we did up here. And I went ahead and used the fifth one. So I used a to the 5 here. Okay. So for 8, again, these are 3 units apart, because 8 minus 5 is 3. So I just kind of did this. We have our r, third power. The fifth term is 81 over 4. And this here is just, some real quick arithmetic. You cube it, so 3 cubed is 27, 2 cubed is 8. Multiply across, and we get 2187 over 32. And that is it for this one. Okay, so nothing too crazy. A few calculations that are, a little bit bigger than normal, but nothing too bad. Okay, I think we have just one or two more left. Oh, we have two more, and they're not too bad. We have the sum of a finite geometric sequence. So the sum of a finite geometric sequence means that it's going to end at some point, right? Here is given by the following. You have your sequence, and the common ratio cannot equal to 1, because then this wouldn't work over here. And it's given by the following. I just keep yawning today. It's given by the following: the summation from 1 to n, whatever that finite number is that you're going up to, of our geometric sequence, okay? And to kind of simplify this, what we do is we just take our first term, we multiply it times the the quotient of 1 minus r to the n divided by 1 minus r, okay? And there's actually a proof for this. Maybe we'll do it. We'll see. We have time, okay? Not in the video, but in class. So let's jump right to it. We have find the sum for the following. From 1 to 10, here's our sequence. So what I'm going to do is I'm going to first identify what A1 is and what R is, because you need those. Basically, we're going to use this formula, but you need these ones to plug into this. And let's find N2. Why not? Because some people are not sure about that. So let's specify. Okay. A1, A sub 1 is going to be the first term, which you'll notice is basically the one right in front. So this one is the same as that one. So it's just 2. Okay. My ratio is usually the one in the parentheses, but it's the one that's has a power to it. So 0.25 is our ratio, or 1/4 if you want to use a fraction. Let's not complicate our lives right now with that. And then n is the number, so 10, 1 to 10, it's just 10. So we're going to use all this, and we're going to plug it into our formula, a sub 1, 1 minus r to the nth power over 1 minus r. Okay. And that is going to give us the following. Let's see if I can get this to fit here. We have a of 1 is 2, and then 1 minus my ratio is 0.25 to the 10th power over 1 minus 0.25. And I'm going to simplify what I can without using a calculator first, because I'm going to have to use it for this one probably. But we have 2 times 1 minus 0.25 to the 10th power, put that in parentheses, over 1 minus 0.25 is like saying 1 minus a quarter, so it's 0.75. And then at this point, it's back to the calculator. So let's do that super quick. And here's my calculator. Let's plug it in. We have 2 times, let's see, we're going to put another parentheses just so that we're clear. 1 minus another parentheses, 0.25 to the power of 10. You want to be real careful with all the parentheses here. Divided by 0.75. So basically, wherever you have like a term, so think of it like this: you have all of this is a parentheses, this is a parentheses, and then I have the whole thing in parentheses. Just be careful with that. Make sure that your calculations match what you wrote here. If you have something weird going on, you might want to double check, okay? So it looks like it's equal to 2.67. And that is it for this one. Very simple calculator stuff. Just got to set it up right, okay? Last but not least, we do have one more example with two parts to it. It says the sum of an infinite geometric series. So the infinite ones are the ones that go on and on and on and on, and they usually will come really close to a number of some sort, okay? Kind of like a limit, but we're not going to talk too much about that. Um, so here's how it works. If the absolute value of r is less than 1, so kind of like a fraction or a decimal less than 1, okay, then the infinite geometric series of this has the sum of basically our first term times r to that to some power. And we can denote it simpler with this little formula. The first term divided by 1 minus the ratio. And that's it. Easy as that. So let's look at our two examples here. So I can get this all in the same. Oh, could be a little tight here. All right, so we're going to look at letter A. Trying to get it straight here. And the formula again is A1. Here I'm going to put it, I'll put it here. A1 over 1 minus R. So that means, I'm just going to kind of put it there on the side. That means that I need a sub 1, which in this one would be 5 because it's the first term right here. And I need my R, which is the one in the parentheses, 0.5. I don't know why I put a parentheses. You didn't have to do that, but it is what it is. So we're going to have our first term 5 divided by 1 minus 0.5. We're just plugging it in. And I think I can do this in my head. See, 5 divided by 1 minus zero point 0.5 is 0.5. And this is just saying 5 divided by a half. So logically speaking, how many halves do we have in 5 wholes? Well, we have 10 of them. If you don't believe me, plug it in. See if you get the same answer. Okay. That's it for that one. So let's look at letter B. It says 5 plus 1 plus 0.2 plus 0.04 and so forth. So this one's a little bit problematic because we don't have the ratio. We have A1, our first term is right there, but we don't know what the ratio is. But we do have some terms, so all we have to do to find R is do some division, yeah? And as a reminder, here is the little kind of formula, I guess you could say. Um, we really typically just have to do one because they should be the same, but we'll do a few just to make sure. So second term, 1 divided by 5. Third term over second, so 0.2 divided by 1. Fourth term, 0.04 divided by zero point 0.2. So supposedly these should all equal to 1/5. Well, let's see. Well, 1/5 is 1/5, so you can't do anything with that. Zero point 0.2 divided by 1 is 0.2, and zero point 0.2, if you change it to a fraction, is 1/5. So we're good. 0.04 divided by zero point 0.2, it's like saying 4 divided by 2, which is going to be 2, but you have these decimal spots, so it's going to move it over and that's going to give us also zero point 0.2. So again, if you didn't follow this part, it's like saying 4 divided by 2 is 2. The decimals kind of like just have one spot moved over because I know there's 3, but you're dividing, so you just consider the 2 on top. It's like saying one of the decimal spots cancels, if you want to think of it that way. So 1, 2, and we get zero point 0.2. Okay. Oh, I'm sorry. Yeah, one of them canceled, so we just have the one spot. So we're good. Okay. And again, you can check it if you don't believe me. So our R looks like it's going to be equal to 1/5. We can go ahead and plug everything in now. Remember that the formula is over here. So we have our first term, 5 divided by 1 minus 1/5. I'm going to use a fraction this time, which is 5 over 1 minus a fifth. Think of this as 5 over 5 is going to be 4/5. Okay, and that would be, let's see, 5 times flip this, so 5 over 4, which is, see, 5 times 5 is 25 over 4. So that's going to give us, I guess we can leave it as a fraction. No, let's do a decimal. So 25 divided by 4 is 6 and 1/4, I believe. Okay, I'm going to check that one just in case because it's late on a Friday. So, chances are I might mess up here and there. Yeah, we're good. There you go. Oh, a little too excited there. 6.25, which is 6 1/4. So we are good to go. And I think that's it, guys, for this video. If you have any questions, as always, please let me know.